Thank you for the introduction. So as was mentioned, I'm going to talk today about efficient ML by approximation. And so I need to give it a couple definitions here. One is approximation, but also why do we have approximation as an opportunity? And that is because I believe, or at least I've seen, and something that we're seeing broadly across software systems, is that our traditional understanding of software is moving away from our discrete, deterministic view of the world where software does just one thing. And instead, it's moving more towards uncertain computation. So let me give you a definition here for both uncertain computation as well as approximation. And the way I like to explain this is actually going back to a class I was teaching a few years ago on computer systems engineering. And I was sitting down with the students, and we are taking a look at this cartoon diagram that I have here of the computing stack, going from hardware up to the application. And what I was asking the students is, why don't we take a moment and think about, which layers of this stack do you trust? Trust to be secure or to produce the correct answer, right? And so we were going top to bottom, and we started with applications, and the students all said, no, I don't trust my applications. I write programs, I write applications, they have bugs in them, so I don't trust them. I know this isn't going to work. Same thing with libraries. At a layer down, we have the compiler and the runtime system, key elements of your software stack that are translating that high-level language down to this low-level machine. And it may not be obvious or familiar to many of you that there are errors at that level, but people coming from my discipline do actually know that there can be critical issues at the compiler and runtime system level. Below that, we have the operating system. I think we've all used Windows, so I think we know there are bugs inside of our operating system. And of course, beyond just Windows, don't want to use it quite as such a whipping boy, but many of our operating systems have issues that we run into in our day-to-day. Now, where things got interesting is when we got down to the hardware system. And I asked students, what do you believe about the hardware system? And they said, well, yes, of course, I trust it. This was pre-Spectre and Meltdown, if you've heard those types of issues before. But they said, if I have an instruction, 1 + 1, and I want to execute it on the machine, it's going to give me 2. It's going to give me the right answer. Unfortunately, that's not true. This may come as a shock to some of you, but what you can do is actually go to Intel's website and download the errata for the processor that's sitting in the machine that you're staring at right now. And what it will tell you are all the things that are wrong with the processor that's in your machine. Some of these are going to be relatively benign. So unless you're doing low-level performance engineering, really trying to squeeze the performance out of your machine, that top issue that I list there doesn't really matter. But this one here at the bottom can affect many, and in fact, all of us. And what it's saying here is, while it may sound a little benign, but our system may cause unpredictable, or our chip, or you may experience unpredictable system behavior. What this really means is that your program or your system can compute and return arbitrarily incorrect results at time. And this happens in practice. So at the consumer level, if you're really stress testing your machine at times, you'll find that every so often your computations actually come out incorrectly. Where people really care about this is actually at the supercomputing level. So our large government entities like the DOE that are doing large-scale simulations, scientific simulations, it's very common for them to see these types of bugs and issues show up because these are large distributed computations running across tens of thousands of processors, and the probability that one processor or one little element in that processor or the memory goes wrong in that entire machine is actually quite high. So these types of reliability issues are a first-order concern in designing these types of systems. And as well, if you're interested, both Google and Facebook put out some very interesting papers in the last year accounting some of the issues that they're seeing in these types of silent errors. So now the question is, if this is the reality that we sit in, that our software, or at least our hardware, produces incorrect results, how do we cope with this problem? Now, what are some of these entities doing? Well, and the errors I want to talk about here are transient errors. And what that means is if I run a computation once and I get an error, if I run it again, then with high probability, I'm going to get the correct result. And so in this environment, the classic thing to do is what's called replication. And so what you do is you take your computation and you're going to replicate it. You're going to have 2 or more copies. You're going to run these copies. And if the results disagree, you're going to go ahead and then run them again until they agree. Now, if you chase this idea back through the history of computing and when it first came into the computing literature, you'll find some work going back to von Neumann back in the 50s, where he was trying to get reliable computation from unreliable components, where quite interestingly, if you look at that paper, these unreliable components really look like neural networks. And this actually connects to a core issue that we're seeing in our computation now, or computations today, is that we're developing computations that are very much, let's say, tolerant or can interact with error and perhaps can still recover useful computation even in the presence of these types of errors. And in fact, let's actually look at this type of phenomena. What happens if we do let errors happen? The example I want to give here is the following. So I've got some code here. You don't at all need to understand this code. But what this code does, it is an implementation of a very simple method for solving systems of linear equations. So much more sophisticated versions of this would be used in large numerical simulations, again, computational chemistry, physics, may be used, for example, variants of this inside of machine learning as well. But the key properties that I want you to understand here are, one, that it's an iterative algorithm, somewhat traditionally like we see in our machine learning computations, where they're computing a number of iterations, and over time, our answer gets refined to be better and better. The second thing that I want you to notice here is I've got some operations highlighted here. And the reason why I've highlighted these is I want to show you what happens when we inject errors in these operations. And so here it is. So what I've got here is an illustration of the behavior of Jacobi as we execute it in two configurations. So the blue line here is what happens when Jacobi is executed on reliable hardware, no errors. Just assume no errors have happened. And it behaves as we might expect when we see from these large iterative solvers, where we start with high error, and over time we slowly converge to low error, or the right answer. Now, the other configuration here is the one on the red, or in the red. And what we've done here is at iteration 10,000 is we've injected some error. And so what we can see here is that, one, this error actually looks quite catastrophic at the outset. We've really jumped up. So based on the errors that we've inserted, we've really jumped up the amount of error that we have in our overall solution at this moment. And in fact, it looks like we've lost 5,500 iterations of progress. However, if you let this computation continue to run, what you'll find is that it eventually still gets to the right result with only about 2.6% overhead, 2.6% more iterations, right? Even though this error hasn't happened. And so what this gives us is a really unique opportunity. One, we can replicate, as we talked about. And so if you were to replicate this computation, and if you dig through the literature and try to find out the best techniques for doing this, you might see something like 50% overhead of system overhead, resource overhead. Not quite as bad as you might expect, where it's going to be 2x, but you can get it down if you do some clever things. But approximation here, if we just let errors happen, well, this is great. We can get 2.6% overhead. But there's a caveat here. The intermediate results, or in general, the final results, may differ by some epsilon, right? They may be epsilon different from what we had expected before. And so this is the definition that I like to work with for uncertain computations, and where I think pretty much all computation is headed these days, where we have results that are computed to a given imprecision or a given inaccuracy epsilon. And what this epsilon actually gives us, right, it sounds scary because typically we don't think of epsilons in our computations unless you're doing numerical analysis, for example. But what this gives us now is an opportunity to exploit this epsilon. If we understand this as it exists, we can start to play these games, like letting errors happen and try to recover a solution that still gives us an epsilon accurate answer, even though it may be different from the original one that we thought. Now, this type of uncertainty is absolutely everywhere at this point. It may not be all that obvious to some, but it is here, and there's going to be more. So at the hardware system level, we're seeing very interesting current and future systems that are coming along with approximate and statistical computational substrates. Reduced precision, we're seeing this show up in a lot of the modern machine learning accelerators with brain float, for example, other different floating point representations. We're seeing opportunities for stochastic, analog, and quantum computation. All of these have epsilons in them. They do not produce a single correct answer. Right? Now, coming up from above as well, we've got uncertainty coming towards us. In our application level, and in particular, our applications are now settled in this uncertain environment, something that we oftentimes don't think about as computer scientists. But what is this environment? Well, if we take as an example something like an object recognition algorithm and application that we have, what it's trying to do is reconstruct the location of objects in the scene. And, well, this environment is only partially observable, right? I mean, the whole problem here is we don't actually know the exact locations of these objects, and we want to figure out where they are within some epsilon. The way that we're going to do this is via sensing in data that is inherently noisy. It's got an epsilon associated with it. And then even as well, the models that we're using to try to construct our estimates of where they are only correct with some given probability, right? And so what this means is that these uncertain computations really are everywhere. It's not computer vision, just computer vision. But it's quantum computation as we're seeing it, image processing, and machine learning as we're all talking about today. Now, the reason why this is so interesting to me, though, and something that I've worked on in my group and with others, and many people in academia and now industry are working on, is because it gives us this opportunity to now trade precision or this inaccuracy for increased efficiency. Right? We've now got this trade-off where we can trade time or resources for the quality of our results. And if we build this in naturally, we can start to navigate our systems towards very different and more efficient directions. And again, you're seeing these techniques come about everywhere. So as I talked about, the approximate and statistical computational substrates are all designed in this model that these are more efficient than a more traditional digital processor. We're seeing this also at the application level, or not the application level, but everywhere in between the application and you and the hardware. Quantization, seeing automatic techniques for quantizing neural networks, or even traditional applications where we're taking your data structures and representing them with fewer bits. We're seeing opportunities for code replacement, take a piece of computation and replace it with something that's an approximation that is more efficient, or even code perforation, where we take pieces of code in your application and entirely throw them away, replace them with zeros, for example. Or synchronization-free parallelism. And this is something that showed up very prominently in certainly some of the earlier stages of machine learning development, where we're looking at asynchronous parallel distributed systems where we have multiple workers coordinating to train a model, but they're not using traditional mechanisms like locks, for example, to synchronize. Instead, they're all racing against the data, providing inconsistent updates, but overall, the system still can converge to a useful and productive result, and do so much more efficiently than otherwise. And then finally, coming up to the application, right? I mean, we've talked about all these techniques where essentially we assume in some sense the application is fixed, and then the ground below us is moving around, but there are opportunities to actually change the application and change the algorithms. So for example, subsampling our data, considering things like statistical algorithms, and many other techniques. And this is the jumping off point where I want to talk about some of the work that we've done in our group on actually changing the algorithm and changing the algorithms behind neural network training. And so the insight here, of course, I mean, actually, this isn't a new insight, but the observation here is neural networks are quite large, very, very large, but very, very capable, right? I mean, this is many of the reasons why we're all here today, where we're seeing these impressive, truly impressive results coming out of models like GPT-3, the Codex models, where essentially we now have neural networks that can talk to us, they can generate code for us, they can have this very interactive and dynamic and multimodal interaction with us and generate all of this very interesting computation. So this is truly powerful. However, it's coming with some significant costs. In terms of data size, and we just saw Antonio talk a bit about that, these models consume a significant and not amazing amount of data. They're also incredibly large in the size of the computational fabric that we even need to be able to store them and even process on them. And as a result, they are becoming essentially prohibitively expensive. Only the largest tech players are really able to play these games and actually participate in this type of technology. And so there's this open question. How can we make this more efficient? I mean, that's why we're here today. How can we actually bring this technology into the reach of smaller players or just less resourced players? And the work I want to talk about today is some of the work that we've done on the lottery ticket hypothesis, where the core observation is that we can take some of these large neural networks, I've got this cartoon of a neural network, and actually find subnetworks, essentially subsets of connections, that we can train to be as equally accurate as the original large network. Now, to explain this and give a little tutorial on pruning, because that's where we derive some of our techniques and get to our ultimate observation here. But the core idea behind pruning is what we want to do is reduce the size, the extent, the weights of a network by removing superfluous or unwanted parts. I'll start to define a little bit of this more in a few slides. But this actually has quite an old history inside of neural networks. So going back to the 90s, and even a little bit before this, there were some great foundational papers foundational and well-titled papers in how we actually reduce the size of neural networks by eliminating connections or neurons inside of those neural networks. More recently, Sung Han, who was at Stanford at the time, is now at MIT, and you'll hear from him later today, actually demonstrated that some of these old techniques were very well applicable to the modern neural networks that we've been working at today. And to explain how this works, let me just walk through a bit of what goes on inside of these techniques. So pruning. So step 0, actually, in any of these neural network training mechanisms is to have a network and randomly initialize the connections that you have between these neurons. That's step 0. Step 1 is then train the network. So apply your standard training regimes to train that network up to the accuracy that you expect for the application that you have at hand. Step 2 is going to be remove superfluous structure. So let me now start putting some definitions in place. One is structure. What is structure? Well, there are many different structures that we have in a neural network. It can be weights, it can be neurons, it can be filters, it can be channels. There are pruning techniques that eliminate essentially all of these and even more of these structures, and they try to understand which structures can we actually remove. The work I'm talking about today and a lot of the work that we've done in our group, we've primarily focused on weights. But again, many techniques in literature looking at these different structures. Now, what does it mean for one of these structures to be superfluous? Well, we can look at the magnitude, let's say, of the weight that you have there, or the activation, or the gradients that are falling on this particular structure as you go through training. Right? And again, techniques in the literature that look at all of these different evaluations for superfluous. And we take a very simple approach. So we're going to talk about you today, and even in some of our work, where we're just looking at the magnitude, again, of the weights that we're going to have in our network. Now, we've removed that structure. And step number 3 is going to be to fine-tune that network. So when you remove structure, what happens is the accuracy of that network is going to degrade, typically. And what you need to do is do a little bit more training on the original data set to recover the accuracy that you had lost. But it's possible, and typically possible, to restore quite a significant amount, if not all of the accuracy that you have. And then finally, there's another step where you can do this iteratively. Keep pruning, pruning and training, and pruning and training, and removing and training over and over again to get a high-quality, compact model. And this truly is the case. So if you look at some of the results that have been out there in the literature, again, going back to 2015, some of these have improved since that time. But what you find is that with roughly similar accuracy, we can get networks that are an order of magnitude smaller. Again, this is going to be after training. So you train your network, and then you're going to prune it and get a much smaller network. So this is wonderful. The community has demonstrated at this point that there's a good number of opportunities to actually get smaller models, at least for something like deployment and inference after you've trained them, using techniques like pruning and in combination with other techniques you might have seen out there, such as quantization. Now, this is great, but what about training? In particular, if we can prune models after training, can we actually train smaller models from the start? Like, why not? What's fundamentally different about these two models? Well, they are quite fundamentally different. In particular, we need to think separately. So pruning after training, we're thinking about the capacity to represent some function that has been learned. For pruning during training, or even before training, we're thinking about the capacity for learning. Does this network have enough capacity or size to be able to learn? So these are, in fact, two very different concepts, thinking fundamentally about what's going to be happening to the underlying mechanisms of this network in this overall training process. Now, as I mentioned in our work, we've actually started to tackle this training problem, moving away from pruning after training, now pruning during or even before training in some of the work that we've done. And the observation that we've had is, quite surprisingly, weights pruned after training could have been pruned before training. And our contribution here is that it's possible to find a network or a subnetwork of this originally initialized network. Again, it was randomly initialized with no intelligence in those weights. That's going to train just as well. So now how does this work? Well, so what we have here is a technique that's called iterative magnitude pruning. And the way this works is, as we started out before, randomly initialize the full network. We're going to train it, and we're going to prune the superfluous structure. Right? So this is actually sounding very familiar to where we were. But where we're going to make a distinction here, at least from the scientific perspective of understanding what's possible, is what we're going to do is we're going to reset each remaining weight back to its value from step 1. So again there, what we're doing is essentially finding some substructure at the end of training via traditional pruning, and then taking that substructure and then porting it back to time 0 before we actually started any training to begin with. All right. So now what that leaves us is, again, is a smaller subnetwork of this original initialized network, randomly initialized network, that of course we can then repeatedly try to do this process just as we've done before, with the ultimate result being that, again, we get this smaller subnetwork of this original network. Now, as a summary, what we do is via this technique, we find that subnetworks can train from initialization to full accuracy at non-trivial sparsities. Right? So we're actually able to use this technique to find significantly smaller networks. And what we mean here is by non-trivial is that oftentimes these networks, they have some residual overcapacity. Sometimes this is called overparameterization, where if you just randomly chose a subnetwork, it can sometimes do OK, depending on the size of that network. Typically, it's usually only about 20% smaller. Once you go less than 20, or you get more aggressive than reducing more than 20% of the size of the model, then accuracy starts to degrade. Right? So the models that we're finding are instead 10 or 20% of the size of the original network. Now, as some results, just to see how this plays out in a very simple setting here in this setting, and of course we have results looking at a wide variety of different domains and different network architectures, but this is one where it's easy to see quite clearly what's happening. But what I've shown here, somewhat similar to what we saw with Jacobi, this is going to be a training curve. On the x-axis, we're looking at the number of iterations that's going on during training. On the y-axis, we're looking at the test accuracy that we have in the model. And over time, the model gradually improves, right? Or significantly and then gradually improves to this accuracy that we care about. Now, this blue line, this is the model with 100% of the weights remaining. So this is just the standard model. We've removed nothing. And now what I want to do is introduce some lines where we've started to remove some part of these networks. And so this first one here is with a network of half the size, so only 51% of the weights remaining of the original network. And what we see is this network reaches roughly the same accuracy and also trains a little bit more quickly. If you go down to 20% of the size, you get a little bit more accuracy, in fact, and it trains even a little bit more quickly, even just measured a number of iterations. Now, of course, this doesn't go on forever. You know, the zero network, that network with no weights, isn't going to do anything for you. But when we get all the way down to about 3.6% of the weights remaining, what we can see is now we have a network that is equally accurate, trains just as quickly, but is now an order of magnitude smaller than that original network. Now, of course, as I mentioned, this can't go on forever. When we get down to 1.9, we start to lose accuracy. But nonetheless, we can see that there is some opportunity here to make these networks significantly smaller, yet still train. And as a summary, so what we find here are subnetworks that train from initialization to full accuracy at non-trivial sparsities. Some of these names may mean things to you, or maybe they do not, but various different computer vision benchmarks. We've also now more recently looked at opportunities in NLP. There are other people in the community who have built upon our results and demonstrated this for various reinforcement learning tasks. So our observations here have actually been embraced quite broadly, and other people are now exploring this in many different domains. But even within our own work, we've robustly tested the hypothesis on not only a number of different model architectures, but even various different ways of training these networks using all the fancy optimization techniques that you can see that are out there. So now, these results, they give us to really the statement of the lottery ticket hypothesis that we've had it, which is that dense trainable networks, these networks that we use, they're essentially fully saturated. They have sparse, trainable subnetworks that are equally capable. And so what this means is they have fewer weights. These weights are typically sparsely connected in their structure, and they reach the same accuracy in the same number of iterations as that original model. Now, there are some caveats there when we're thinking about particularly going towards things like efficiency, true wall clock efficiency, right? So we're finding these subnetworks retroactively, as I explained it, right? We trained it, and we did this pruning process, and we backported this mass to the beginning, right? So this is, we haven't realized this promise quite yet, though there's active work in this area. Also, finding these networks, subnetworks, is very expensive. That fine-tuning and iterative training, retraining process, that is not cheap, though, again, we've had work in progress and others on making that much cheaper. And then finally, eliminating weights just by itself does not necessarily equal better performance without also software and hardware support. Right? So depending on the structure that you choose, you need to co-design the software and hardware underlying that. So essentially, your GPU, as well as perhaps your PyTorch or TensorFlow, to be able to really harvest the performance that you're getting out of that. So this is all not just an easy task, and it's not yet fully realized. But there's a lot of opportunity here, and we've been chipping away, along with others, at this block. And just as an example here to close out where we are, what I've got here is we can conceptually think about standard training of our neural network as approximately like this. Again, x-axis, epochs of training, alternatively iterations, and then y-axis is the number of weights remaining in our network at that point in training. Our standard training means we keep the entire network around throughout the entire course of training. There are a variety of different techniques that are now out in the literature thinking about gradual pruning, where you start out with your full network, and then you gradually reduce its size down to the end. As I had talked about before of non-trivial sparsity, sometimes you can just randomly throw away weights at the very beginning. And that'll get you to something that's typically somewhere between 60 and 80% of the size of the original network. And that can be an alternative strategy, and in some senses, the naive benchmark that we'd expect in this space. But with our work, what we've shown, at least at scale, is that for very small amount initial training where you keep the whole network around, it may be possible to, again, drop down to essentially a network that's an order of magnitude smaller than the original. And so this is our opportunity. Thinking about the area under this curve is what we want to minimize. The smaller the area, the more efficient that we're going to be in this process. And there still remains quite a significant gap between what's possible and where the current techniques are in the day. And this is some work that we surveyed just last year, and of course, making progress on going forward. So to wrap up, what I've talked about today, at least in the small core technical part, is efficient ML by pruning, perhaps by changing the algorithm. But early in training, there exists these small, sparse subnetworks that are just as good as our original networks. And this has had and continues to have strong implications for both standard training and things like transfer learning, where perhaps we learn these small networks and then transfer those networks to a different problem. Many people in the literature have actually shown at this point that that can be a productive way to reduce the cost of training on that secondary task. And then finally, there are still open challenges on the software and hardware side. But even to take a step back up to the top level, right, the future is changing. The future of software is changing. Everything is going to be uncertain. I know we don't like uncertainty as humans. It's difficult to navigate. And as computer scientists, one reason I would say computer scientists love being in computer science is because typically the world has just been discrete and exact, and you can completely reason about that world. It's kind of comforting. You get to escape the real world, right? But the real world has been coming for computer science, right? And that's what we're seeing in the modern integration of machine learning methods, where these applications are now deeply interacting with in uncertain environments and uncertain hardware. So this is scary, but it's also an opportunity. Right? This is a massive opportunity to put in place methods for approximation, as I've shown today. And there are many people in academia, as well as a few players in industry, such as the company that I've been working at and advising, Mosaic ML, where we're really thinking very hard about how we can approximate and essentially change the semantics, change the math behind our systems to get better results. So, thank you. All right. We have a few questions here. Are we sure that the pruned neural network exhibits the same performance, especially the same false positive rates and same robustness? This is a wonderful question. So there has been an active effort over the past year or so to actually understand measures of evaluating the behavior of networks beyond just accuracy. And what's interesting here, so there's some initial work that actually came out of Sarah Hooker. She did some work along with a group of collaborators out of Google, where they demonstrated that actually these types of techniques can have different impacts on different subsets of the data that you have. Some of this work as well was followed up by some work that went on at MIT by Lucas Libetzwin. I can't remember his last name, sorry about that. But as well, showing that there can be disparate impact between different types of examples that you have in your data set. We have some follow-up work right now in this space as well, but broadly what I would say is that accuracy may be the same, but as we put in additional robustness, let's say measures of robustness or measures of alternative characteristics of our network, things may actually be slightly bit different, right? And so this is very much an active area of research, and there's been no definitive conclusions right now, but people are starting to show that we need to take a more holistic view of this, particularly in concerns with measures of fairness that have become of prominence lately in the community. What problem is the inspiration for this research? Well, there are a couple ways. I mean, sometimes it's not a problem to research. Sometimes it's just curiosity, right? I mean, quite truthfully, sometimes it's what happens if we do X to this entity, right? So there's actually quite a wonderful thread right now in machine learning of just doing empirical machine learning, where we're starting to realize that these artifacts that we're developing are essentially scientific or natural artifacts, where what we want to do is just understand more about their behavior. And this observation that we could remove things, which was found somewhat by accident, became very surprising and a deep thread that we wanted to investigate. However, of course, the problem of efficiency and our networks being out of reach is another motivating factor here as well. Cool. All right, thank you.